Hi everyone again. This is part 2 of the videos in which I solved the problems that we had for practice for test 2. Okay, so we'll continue with that and we're on to question number 4. What are we told? The expected number of defective air conditioner units manufactured by a factory is 0.5 every day. What's the probability at least 2 air conditioners manufactured next week are defective? Okay. So now what we want is to find the probability at least 2 are defective next week. So you ask yourself, what kind of random variable is this? And you see the expected number of units that are defective is just half every day. These kind of things are not common occurrences, so you think that this must be a Poisson random variable, where lambda is 0.5 per day. Then the question is about the week. So we have lambda is 7 times 0.5, assuming it's a 7-day week per week. Okay, so now what do we have? Let x be the number of defective units next week. Then we want the probability of x is bigger than or equal to 2. One thing I wanted to mention. Why is lambda 0.5? Because for a Poisson random variable, the expected value is lambda. Okay, and we're told that the expected value is 0.5. Okay, anyway, so lambda 0.5 per day, so lambda is 3.5 per week, and our question is about the next week, so let x be the number of units manufactured next week. The question is, what's the probability at least 2 are defective? So this is what we have. So it's easier to look at this. And you know, for a Poisson random variable, it is e to the minus lambda, lambda to the k over k factorial. So this is 1, that is 1. So factor out e to the minus lambda, and you will have a 1 plus lambda. Or if you don't like that, you could leave it as 1 minus e to the minus lambda e to the minus lambda, whichever way, that's fine. So that's it. That's the answer. All right. Let's move on to the next problem now. We'll look at question number 5. Okay. So what are we told? The distribution of a continuous random variable is given by this. F of w equals e to the minus 1 over w if 0 is less than w. So it's w is bigger than 0 and 0 otherwise. All right. So OW is common notation for otherwise. And we want to find the density function. So we want F. But what do you know? You know that this is just a derivative. So what will it be? What is the derivative of that? So e to the minus w raised to minus 1. So we'll have e to the minus, same thing, times the derivative of this, which is minus stays, w raised to minus 1 is minus w raised to minus 2. So, and 0, otherwise derivative of 0 is 0, so this is when omega is bigger than 0. So that's what the density is, all right? Just we had to use a chain rule. Okay, and then, you could have been asked, what is the expected value, etc., but in this case, you would not be able to find the expected value because you would end up with an integral that you can't compute. So, you could set up an integral for this, and just here's the integral from 0 to infinity omega times e to the minus 1 over this. So that's the integral. That is the expected value, but you just leave it like that, or maybe you can do a change of variables, but still you won't get something that you could integrate easily or at all. Okay, but anyway, that was just a digression over here. What we're asked is just for the density. Okay? All right. Now, let's go on to question number 6. Okay? I mean, in this question, you could be asked something like, okay, sorry, back to this. What if you're asked, what is the probability that, let's ask, what if I asked you that? Okay? So let's come to that. That's what is the probability W is bigger than 3? Well, that's 1 minus the probability W is less than or equal to 3. But what is this? This is just the amount of gold to the left of 3 like we spoke of, or the cumulative distribution function evaluated at 3. So it's 1 minus e to the minus 1/3. Okay? So it's easy to do this. You don't have to, if you're given the CDF for finding out something like this, you don't need to do an integral. All right, so that's just an aside. Okay. All right, so now let's move on to number 6. Okay. You roll a pair of fair dice 8 times. What's the probability that you roll a pair of identical numbers at least 2 times? Okay, so real quick. Identical would be in those spots, right? There's 2 different dice, so let's just... So what's the probability of rolling an identical it is 6 over 36 or 1/6. Okay, and you're told, so this is going to be your P for the variable we look at. You roll a pair of fair dice 8 times with the probability that you roll a pair of identical numbers at least 2 times. So what are you interested in? The number of times you roll a pair of identical numbers, right? So the random variable you're interested in is that, okay? So let X be the number of times in the 8 rolls. So what are you being asked? What's the probability? X is at least 2. Same kind of deal. Okay, and what kind of random variable is X? Okay, we've labeled it. And we know that X will be a binomial random variable. N equals 8. P is the probability of rolling a pair, and that is 1/6. All right, so it is 1 minus 8 choose 0. P raised to 0, which is 1/6. 1 minus P, which is 5/6 raised to 8. Minus 8 choose 1. P raised to 1. 1 minus P raised to 7. That looks like, yeah, let's not put parentheses there. Okay? So just simplify it. 1 minus 5/6 raised to 8 and then minus, that's an 8, and 5 raised to 7 over 6 raised to 8. I mean, we could write it like that. It doesn't matter. Okay, so that's that probability. All right. So on to number 7. Okay. A discrete random variable, y, has its probability mass function given by this below, where k is some constant. Find expected value of y in terms of k, and you're asked, is variance a finite number? Okay, so this is a discrete random variable. What is the formula? That's the formula for the expectation. In this case, the probability mass function you're given is that. Okay, so I wrote F, I could have written P. All right, so it's only non-zero from 5 on. Okay, n times P of n, which is the f of n in the question. So this is a geometric series now. 1/4 raised to n, that's your common ratio. A is k, and what is the first term? 1/4 raised to 5. Okay, so just rewriting it. If you want, we write 256. Okay, so that's the answer. All right. So that's the expected value of y, and since k is a number over here, it's just that same number over there. Okay, obviously you know k is non-negative because you have that it is part of the mass function. Okay, next let's think about what's the variance of y. The expected value of y squared minus the expected value of y whole squared. So this we know it is k squared over 768 squared. How about the expected value of y squared? What is that? It'll be the sum n squared times f of n. So what is it? It's the sum. Actually, maybe I should. N squared times k over n times 4 to the n. Okay. Okay, so what will that be? All right, now look at this series. What do you have? That's just the expected value of y squared. Okay. What do you have in this series? You have n over 4 to the n. You know, looking at this series, the numerator grows at a much slower rate than the exponential function in the denominator, and by you could use the ratio test, for example. You know that this series converges. And thus you have that the expected value of y squared is finite, and you know that the expected value of y whole squared is finite, so the variance is finite, okay? separate. Okay. And that's expected value. All right, the second part over here is really me just showing you that what you have over here is a random variable whose variance, when you look at the variance, you have this series that you have to study, expected value of y squared, and you know, your knowledge of series comes into play and you know that that is finite. All right? Okay, so now let's move on to the next question, number 8. You could think about this question actually for a moment. I've asked you if the variance is a finite number. Is it possible to have a variance that's infinite? Can you try and come up with a random variable that has an infinite variance? Okay, try and come up with a discrete random variable that has an infinite variance. I'm not going to ask you that on the test, of course, just something to think about. Okay? All right, so on to number 8. Okay, probability of hitting a target in a game of darts is 0.015. What's the approximate probability that you hit the target at least 3 times when you try 200 times? Okay, now here's the comment on this. So what is going on? You hitting the target again and again and again. You're trying 200 times, right? And each time this is your probability. It's tiny. You're asked what's the probability of hitting at least 3 times. So really, if x is the number of times you hit the target, okay, what do you have? You have that x really is a binomial random variable. N equals 200 and p equals 0.015. Okay? The exact probability is going to be this crazy thing. 200 choose 0. P, which is 0.015 raised to 0. 0.985, which is 1 minus p raised to 200, minus 200 choose 1, 0.015 raised to 1, 0.985 raised to 199, 200 choose 2, 0.015 squared, 0.985 raised to 198. That's the exact probability. But that's some craziness. That's crazy numbers. In this case, I've asked you for the approximate probability. So you have to do an approximation. So you know n is large, p is small. NP, what is NP? Okay, this will be 3. So that is moderate. So this you know is approximately Poisson with lambda equals 3. All right, so the probability x bigger than or equal to 3 is approximately probability of a Poisson random variable with lambda equals 3 bigger than or equal to 3. So that's 1 minus it being less than 3. So 1 minus e to the minus lambda, lambda to the 0 over 0 factorial minus e to the minus lambda, lambda to the 1 over 1 factorial. And that's the answer, okay? So you simplify it, 1 minus 1 over e cubed. And what do you have in the parentheses? You have 1 minus 3 minus 9 over 2, which is 4.5. Okay, so put it all together. No, that's a plus in there. Sorry, I just made a little mistake. That's a plus. So put it all together and you have 7.51 minus. All right, so that's the approximate probability, and you see for the approximate I put double squiggles. Okay. All right, so let's move on now to question number 9. You get bonked in the head with a tennis ball. As a result, you do not quite remember everything. Your friend told you that you just beat him in a club tennis match. In a club tennis match, the players keep playing a sequence of sets till one person has won 3 sets in a row. If you win any given set independently of other sets against your friend with probability 0.6, what's the probability that you beat him in exactly 5 sets? So you have to have 3 wins in a row to win the match. Okay? So what do you have? Win, win. Let's say, let W be the event that win ith set. Okay? So you want W1, W2, W3. That is winning in 3 sets. And if you win in 4 sets, then obviously you have to lose the first. That would be the sequence that has to occur if you're winning in 4 sets. Correct? You could not have a win over here and a lose later because you need the 3 W's consecutive. If you win in 5 sets, let's start from the back. You need W5, W4, W3. How about over there? You cannot have a win, otherwise you would have won in 4. So this has to be a loss. Now what about here? This could be W1 or L1. So, right, makes sense? Because that would give you 3 in a row at the end, and the one right before the last 3 wins should be a loss. Okay? So the question is, or maybe I shouldn't write L. I haven't introduced that, so I should do W1 complement. W1, W2 complement, W3, W4, W5, union, W1 complement, W2 complement, W3, W4, W5. The probability of the union is the sum of the probabilities. Oops. Okay, they're disjoint. And then the probability of each one of these sequences, you can multiply the probability by independence. And then just chuck in the numbers. It is 0.6, 0.4, 0.6, 0.6, 0.6. And what is this? This is 0.4, 0.4, 0.6, 0.6. 0.6. Okay? So what do you have? You factor that out. It is just going to be that's the answer. Okay? All right. I hope that was clear. Let me box the answer. All right. Okay, let's move on to number 10. For a group of 50 people who have September birthdays, compute the exact values of the probability that exactly 3 out of the 50 are born on the last day of September, 9:30. Okay, so let's look at that. So, you have 50 people, you're assuming independence, like you don't have twins, etc., this, that, just they come from different parts, not related to each other. And you want the probability that exactly 3 out of the 50 are born on the last day of September. So let X be the number Okay, what kind of random variable is X? It's binomial, n equals 50. And what's the probability? What's the probability of being born on 9:30? Now, normally you would say 1 over 365. But the thing is, all of these 50, they have September birthdays. You're only looking at people who have September birthdays. So then in that case, this probability is 1 over 30. Make sense? And we want the probability X equals 3. So that is 50. Choose 3. 1 over 30 raised to 3. 29 over 30 raised to 50 minus 3. Okay, so just trying to make it look nice. 400 times 49 times 29 raised to 47 over 30 raised to 50. Okay, so that was the answer to part A. Part B really is using techniques that we'll stress more in chapter 7. But I'll just quickly talk about this. I won't ask you this on the test. So how do we answer part B? Okay. Well, the way you do it is by indicator random variables. I've talked about this before. So let xi be 1. Okay. 1 if ith day of September is birthday of 3 out of the 50. So if you pick any one of these days, so for example, September 15th. So what is the random variable x15? It is 1 if exactly 3 have September 15th birthdays. If 4 have September 15th birthdays, or 2 or 1 or 0 or any other number besides 3 have September 15th birthdays, then this random variable is 0. Okay, makes sense? Okay, so this random variable is 1 if that day is exactly the birthday of 3 people. and 0 if it's the birthday of any number of other people. Okay? And what do we want? The number of days that are birthdays of exactly 3 people. Well, what will it be? You're looking at all the 30 days. And you put a 1 in if it is the birthday of exactly 3 people, and you put a 0 in otherwise. Okay? And then you're counting the number of 1. So you're adding up these xi. So the number this will be the expected value of the sum. Expected value of sum is the sum of the expectation. Now, what is the expected value of xi for any I? Let me write that down here. I need to use a different color so it doesn't squish in your eyes. So it's 1 times the probability xi is 1 plus 0 times the probability xi is 0. It's a discrete random variable, right? So this you can see is just the probability xi is 1, which we know from part 1, for any one day of September, the probability that it's exactly the birthday of 3 people, this September 30th, there was nothing special about that, is this number. Let's call it P. Okay? So what do we have here? This is P. There's a 1 here. This is P. This is P. So it's 30P, where P is exactly that. Okay? So this is really techniques you look at in chapter 7, but in theory you could do it right now too. Okay? So I'm just gonna write it. Okay. All right, so that was number 10. Also did 10b. You know, it's good to have it in your brain, and then when we come back to it, it'll be much nicer for you guys. Okay, now let's move on to number 11. Number 11, we have the density we want to find the density of x cubed when we're given the CDF of the function of the random variable x. All right, so what is the density of x cubed? The way you find the density of a random variable, if you don't have it, but you have the density of the CDF of a different one, the way you find the probability density function of x cubed is via its CDF in the continuous case, okay? So we don't know anything about x cubed, but we know something about x. So what we do is find the CDF of x cubed, then differentiate. That's a cumulative distribution function of x cubed and then differentiate. Okay, so let's just write like this. What is this going to be? It's the probability that x cubed is less than or equal to a. Okay, well, let's take a look for a second. You know that the CDF, let's look at the CDF of x. It is 1 minus 5 squared over x if x is bigger than 5 and 0 if x is less than or equal to 5. Actually, there's a typo here. I'm sorry. This should be an x squared. Okay, all right. So as x goes to infinity, this goes to 0, and as x goes to 5, as x goes to 5, this whole thing goes to 0 and x goes to infinity. This goes to 0, so 1 minus that goes to 1. Okay, so if you just look at the graph of this, it is 0, then it goes to 1. Okay? All right, so this random variable, x, is bigger than or equal to 5. So what do you know? So we see that so x cubed is bigger than or equal to 125, correct? Okay, so what does that mean? All the gold is to the right of 125. Okay, let's draw our line for x cubed. And you know that all the gold is there. Okay, the whole 1 gram of gold. So if you pick any a to the left of 125 and you ask what's the probability of x cubed being less than or equal to a, that's asking you how much gold is to the left of a. That is 0. So you see this will be 0 if a is any number less than 125. Okay, now how about if it's bigger than 125? Let's just rewrite this just for fun. Now we take cube roots. And you don't have to flip anything. And you have this. Okay, so what is this? Take a look. This is the probability x is less than or equal to something. What is the probability x is less than or equal to t? This is just the CDF of x evaluated at t. What's the probability x is less than or equal to a balloon? This is the CDF of x evaluated at the balloon. Okay, so what's the probability x is less than or equal to the cube root of a? This will be the CDF of x evaluated at the cube root of a, right? So that is 1 minus 5 squared over cube root of a squared. Okay, so if you want, write it 1 minus 25 over a raised to 2/3. All right, so that is the CDF of x cubed, right? I mean, not just that. This part combined with this part, this is if a is bigger than or equal to 125. Okay, over here, once we have the CDF of x cubed, the way we get the probability density function, or the density, is by differentiating it. Derivative of 0 is 0, derivative of 1 minus 25 a raised to 2/3. It'll be this over here, put it together, and you get 50 over 3a raised to 5/3. And that's your density for x cubed, actually. Okay. All right. Okay, so now on to the last question, number 12. Okay. You're stuck in a hotel for n nights where probability n equals k is 6 minus k over 15 for each k. For each of the first 3 nights, the hotel charges $300 per night. But after that, their rate drops to $150 per night. Calculate the expected value of the total cost of your hotel stay. Okay, so let's see what you have. You're given the probabilities of being stuck for k days. You can only be, according to this, the probability of being stuck for anything bigger than 5 is 0. And probability of k equaling 0, 0, you either stuck for 1, 2, 3, 4, or 5 days. Okay? And the cost, if you're stuck for 1 day, is just $300. Cost if you stuck for 2 days is 300 each, so it's 600. Cost if you stuck for 3 days is 300 each, so it's 900. What about if you stuck for 4 days? What's the cost? If you stuck for 4 days, the first 3 days it's 300, and then it drops to 150 per night, and same for 5. So that's something you notice in that part that we discussed. It's got nothing to do with probability. It's just thinking about what these numbers are. Okay, so let's make a chart of K, okay? The probability N equals K, that's the probability mass function. And also, let C of K. C of K is the cost function. Okay, so if you want, you can either write over here, you could write P of K. That's normal for the normal notation, standard notation for the probability mass function. Okay, so let's put this down. 1, 2, 3, 4, 5. Okay, maybe we'll spread it out a bit. Okay, so this is plug in K equals 1, and it's 6 minus 1 over 15, so it's 5 over 15. This is 6 minus 2 over 15, so it's 4 over 15. 6 minus 3 over 15, it is 3 over 15. 6 minus 4 over 15, it is 2 over 15. And 6 minus 5 over 15, it's 1 over 15. I'm not simplifying these fractions. I'm leaving them as with division by 15, because later on you'll multiply and add and stuff. So it's better to have the common denominator already. Okay, so now what's the cost if you stuck for 1 night? It is $300. What is the cost if you stuck for 2 nights? It is 600. If you stuck for 3, it is 900. If you stuck for 4, it is 3 times 300 plus 1 times 150. And if you stuck for 5, it is 1,200, right? Okay. So now what is the expected value of the cost? Cost is a function of the number of nights. It's a fixed function. It's not a random function. I mean, in the end, you could call this whole thing the random variable capital C, but this little c function, it's fixed, you know. You have that it's 300 for 1, 600, and so on. So it is like C of K. It is 300K if K is less than or equal to 3, between 1 and 3, and it is 300 times 3 plus 150 times K minus 3 if it is bigger than 3. Okay, so you know that's a fixed function. Okay, all right. Okay, so now what will this be? This is the sum over K. Okay, so it is 1 times 300. Sorry. It is 5 over 15 times 300 plus 4 over 15 times 600. And that it is Okay. So put that all together and if 1,500 plus 2,400, that's 3,900, 3,900 plus 20, I'll just write it out. $39, $66, $89. I mean, 87, 99, right? 66, 87. Okay, and this can actually divide. You have 6, 6, 0. All right, so that's the expected cost. All right. Hope this made sense. What have I used over here? This is just a formula for the expectation of a function of a random variable. What were the key points in this question? Understanding that you're using a function of a random variable to use the formula for that and actually coming up with the function values for the different k values. Okay, so if you want, I can put this in over there to be more specific. Okay, well, I hope that made sense. And I will post the entire PDF of all the solutions. Okay, bye.